It's pretty incredible when you stop to think about it. How you just move. You decide you want to grab your coffee, and your hand just goes. It's smooth, it's precise, it feels so simple, right? But behind that one little action, your brain just performed a lightning-fast calculation, picking that one movement out of a million other things it could have done, and telling every other muscle, nope, not you, stand down. It is an absolutely breathtaking piece of biological engineering.
So how in the world does our brain pull this off every single second? Well, here's what we're going to cover. First, we'll meet the brain's official gatekeeper for all movement. Then, we're going to break down the two main systems it uses. Think of them as an accelerator and a brake. And finally, we'll take a look at what happens when that beautiful, delicate system loses its balance.
So this right here is the central puzzle. At any given moment, your brain is just swimming in potential actions. How does it zero in on the one thing you actually want to do, like reaching for that cup, while at the exact same time shutting down all the things you don't want to do, like, waving your arm or tapping your foot or suddenly jumping up?
Well, the answer lies deep inside the brain, in a collection of structures that act like the ultimate traffic cop for movement. This is where we start. Let's get to know the basal ganglia.
Okay, so the basal ganglia doesn't actually come up with the idea to move. That's a higher level job for the cortex. Think of the basal ganglia more like a bouncer at a really exclusive club. The cortex sends all these different movement ideas to the front door, and the basal ganglia is the one who checks the list and decides, okay, you can go, you can't, you wait. It is the master selector.
To manage this incredible task, the basal ganglia uses this really elegant, kind of brilliant solution, a perfectly balanced push and pull system. It's got an accelerator to say, go for that one specific action, and a brake to say stop for literally everything else.
All right, let's start with the go pathway. This is also known as the direct pathway, and you can think of it as our brain's dedicated gas pedal for the one single specific movement we're trying to make.
Now here is where it gets really clever and a little bit counterintuitive. Your brain's motor system isn't just sitting there waiting for a go signal. It's actually being held back by a constant stop signal all the time. So to get things moving, the go pathway doesn't actually push a go button. It works by removing the stop signal. It is exactly like taking your foot off the brake pedal of a car that's already in drive.
And you can see the beautiful chain reaction right here. It all kicks off when the cortex tells the striatum, hey, I want to move. Now watch this. The striatum then tells the GPI, that's the structure that's normally slamming on the brakes, to quiet down. With the GPI inhibited, it suddenly stops inhibiting the thalamus. The thalamus is now free, and it sends this massive let's do this signal back up to the motor cortex. And boom, just like that, your arm reaches for the cup.
But of course, that's only half the story. Because for every single go signal, we need a really powerful no-go signal for all the other movements we're trying to avoid. And that is the super important job of the brake pathway, also known as the indirect pathway.
Now this pathway, you'll notice, has a few more steps. It's a little more complex, but its goal is pretty straightforward. It works to ultimately fire up something called the subthalamic nucleus, or STN. And just look at the end result here. The STN's whole job is to excite the GPI. Remember, that's the brain's master brake pedal. So a superactive GPI sends a powerful stop signal to the thalamus, effectively slamming the brakes on any of those other competing unwanted movements.
And that right there is the beautiful balance. These two pathways, as this research paper puts it so well, have opposing effects. They're in this constant perfect tug of war. The direct pathway releases the brake for one specific action, while the indirect pathway slams on the brakes for everything else. It's this dance that allows for such incredibly precise voluntary movement.
Okay, so if the direct pathway is our accelerator and the indirect pathway is the brake, who's the driver? Who is skillfully working both of those pedals at the same time? Well, that would be the one and only, the famous neurotransmitter, dopamine.
Dopamine, which comes from this little area called the substantia nigra, is the master modulator of this whole system. It's amazing, really. It acts on two different kinds of receptors. On D1 receptors, it juices up the go pathway. That's like pushing down on the accelerator. And at the exact same time, it acts on D2 receptors to put the brakes on the brake pathway, which is like easing your foot off the brake pedal. It's this incredible dual action that makes our movements so smooth and intentional. So now that we've built this intricate, beautiful machine, let's see what happens when a critical component, our driver, dopamine, starts to go missing. This is exactly what's happening in Parkinson's disease.
In Parkinson's, those neurons in the substantia nigra, the little factories that make all the dopamine, they begin to get sick and die off. And as they disappear, the basal ganglia is basically starved of the one chemical it absolutely needs to operate that accelerator and brake system correctly.
So without dopamine, the entire system is just thrown completely out of whack. There's nothing there to hit the accelerator on the go pathway, so it gets really weak. And there's nothing there to ease up on the brake pathway, so it becomes totally overactive. The end result is a system where the brake is just permanently slammed to the floor.
And you can see this imbalance really clearly right here. The brake pathway is just screaming at the top of its lungs, while the go pathway can barely get a whisper out. This leads to way too much activation of that master inhibitor, the GPI, which in turn puts a massive constant stop signal on the thalamus and any motor command it's trying to send out.
And this isn't just theory. This directly explains the symptoms that people experience. I mean, think about it. If your brain's brake is always on, it becomes incredibly hard to even start a movement. That's a symptom called bradykinesia. All those constant stop signals also lead to rigidity, and this faulty, unbalanced circuit can end up generating that characteristic resting tremor.
So let's just pull this all together. Our ability to just move around, to be free and precise in our actions, isn't about just yelling go. It's about this incredibly sophisticated system of accelerators and brakes, all managed perfectly by dopamine, that selects one movement while shutting down all the others. And when that balance gets lost, well, so does our control.
Which of course leads us to a final and actually pretty hopeful question. Because understanding this broken circuit in such detail doesn't just explain the disease, it gives us targets. Therapies you might have heard of, like levodopa, which helps replace dopamine, or even deep brain stimulation, which can artificially tweak these broken circuits. They're all designed to do one thing: to try and restore that delicate balance and to give control back to the driver.